And our first speaker of the last day is David, who will give us the final installment of Strings in QCD.
Thank you. So thank you everybody for coming so early. Today I want to start by asking the question of how bright is the quark-gluon plasma, the n=4 quark-gluon plasma. What that means is that I want to calculate what's the rate of photon production. Of course, any plasma that carries whose particles carry electric charge in thermal at some finite temperature will emit photons. And I want to see if we can calculate that rate of photon emission. And the motivation for that is that the quark-gluon plasma at RIC is supposed to be what's called optically thin. What that means is that because of the finite extent of the fireball that's created there, and because the electromagnetic coupling constant is weak, once a photon is produced somewhere in the plasma, it escapes virtually undisturbed with hardly any other subsequent interactions. And so it carries very valuable information about the point, like the local temperature, etc., about the point where it was emitted. This is not true for probes which interact through the strong interactions, like the quarks and the gluons, okay? Because they will interact many times before they come out. So that's part of the motivation. The other motivation is that in order to calculate this rate of photon production, we will have to calculate a two-point function of electromagnetic currents. This will allow us to write down and plot a spectral function. And what I want to do is to show you, to back up my statement yesterday, that at least in the plasma of the n=4 theory, once the mesons melt, there are no quasi-particle excitations. So we'll look at the spectral function and we'll see there are no narrow peaks that you can interpret as more or less well-defined quasi-particles. OK, so how do we do this? Suppose you have an SUNC cross U1, where this U1 is a photon, gauge theory. For example, imagine you have large N QCD that has a gauge group SUN. If you couple that to electromagnetism, then the gauge group is SUN cross U1. So for such a gauge theory, there's a standard formula that you can find in textbooks that tells you what is the rate of photon production, d gamma per unit free momentum at a given temperature, and that's given by E squared, where E is the electron charge, if you like, the elementary unit of charge, or the coupling constant, more precisely, for this U1, over 2 pi cubed times 2k. Then here there's the usual Boltzmann factor. And then the interesting part is the trace, eta mu nu, chi mu nu of k. This is all calculated at null momentum. So let me tell you what each object is here. This chi is the so-called spectral function of electromagnetic currents. So chi mu nu is equal to minus 2 times the imaginary part of the retarded correlator, mu nu, of two electromagnetic currents. And that is given by as usual, the Fourier transform, minus I times d4x, e to the minus I kx, theta of x naught. And then there's a commutator of j mu of x, j nu at 0, where J, electromagnetic, takes the form psi bar gamma mu psi, as you're all familiar with. In theories where, like the ones I'll be looking at, where in the fundamental representation there are not only fermions but scalars. Remember, a hypermultiplet also has scalars in it. There are extra terms here, but we don't need to know the precise expression of this current. It's just a conserved current associated to that U1 symmetry. Okay, it's the object that couples minimally to the photon, A mu. So the action for that SUN cross U1 theory would contain a term of the form A mu, J mu, electromagnetic. Is this clear? And this K up here, remember, K is the photon momentum, which is null. So this is K naught, K vector, and K naught is equal to K. Okay. So this expression I wrote down here, this commutator, this, or more precisely this correlator, diagrammatically corresponds to the following thing. You have, this is the external leg for the photon, and then the correlator, this J mu, is this thing here. And what you want to calculate what you want to really calculate is this object in the middle, okay, which of course includes all sorts of quantum effects, such as photons running in here, gluons, and in general any field you have in your theory. So for example, this one here would be a photon, and this one would be, say, a gluon. So we have a problem, because I don't know. So we want to, of course, let me back up for a second. The reason we're doing this is because in QCD, calculating this correlator at strong coupling is not something we know how to do, because we need this correlator in Lorentzian signature. Okay, this is real-time physics. The lattice is not very good for that. So we can't do it on the lattice. And of course, we have no analytic methods to do it at strong coupling. So we are lost. And then the motivation is, well, let's look at other theories for which we actually have a gravity description that allows us to calculate this and see if there are some universal features. Okay? So I want to calculate this using the gravity description. But the problem I have is that I know what the gravity dual to an SUN theory is, but I don't know what the gravity dual to an SUN cross U1 theory is. Okay? In other words, I don't know what the dual to a theory with gluons and a dynamical photon is. However, I just told you that the electromagnetic coupling constant is weak. In particular, it's weak enough for this fireball, the rate of production for this fireball, to be well approximated, one hopes, at leading order in the electromagnetic coupling constant. So what we're going to do, what we can do, is to calculate this object at leading order in E squared holographically. Why? Because in this diagram, if you have not just gluons, but photons running inside the diagram, in the loops, that will lead to higher order terms in E, because each vertex comes with an extra power of E. So to leading order in the electromagnetic coupling constant, okay, this is approximately equal to leading order in E to something where only SUNC fields run in the loops. In other words, I can, to leading order in E, I can calculate this correlator not in an SUN cross U1 theory, but in an SUN theory, for which I know what the gravity dual is. So if I forget about this part and I just look at this SUN theory coupled to fundamental matter, to quarks, this theory still has a conserved charge associated to rotations of phase rotations of the quark fields that leads to a conserved current that takes this form. And we know that ADS-CFT is particularly well suited for computing correlation functions of conserved currents at the boundary. Is this clear? Just like, for example, calculating the viscosity requires you to calculate a two-point function of the stress energy tensor. Here, calculating photon production is a two-point function of electromagnetic currents. But it's exactly, conceptually, it's exactly the same. Any questions about this? Good. So before I tell you how we're going to calculate this, let me emphasize a couple of things. The first one is that I will only calculate this correlator. Remember that the degrees of freedom that are charged under this putative U1 are the fundamental degrees of freedom. So, and I told you yesterday that there is a phase transition between Minkowski and black hole embeddings. Okay? So we have to decide where we're going to do the calculation, on this, in this phase or in this phase. I'm only going to do the calculation in this phase. And the reason for that is that we know what the result is in this phase. Why do we know that? Well, if you're computing a two-point function, and you do that in a phase where the relevant degrees of freedom, where the spectrum of the relevant degrees of freedom consists of a discrete set of absolutely stable particles, then you know that the spectral function, this object here, is just going to be a sum of delta functions located or supported at the appropriate values of momentum or mass for the particles in the spectrum. Let me give you an example of that. Imagine that you have some particle in your spectrum with which is not necessarily absolutely stable. So the retardative correlator has a pole of the form 1 over omega. Omega is the energy, minus omega of k, plus I gamma of k. This is the typical form of a correlator of the two-point function near the singularity associated to the presence in the spectrum of a particle with energy omega, an imaginary part gamma. And so if you plug this into, if you take the imaginary part of that to get the spectral function, chi goes like gamma over omega minus capital omega squared plus gamma squared. So this, of course, looks something like this. Gamma as a function of this combination. So this height is of order 1 over gamma, and this width is of order gamma. So of course, in the limit that gamma is very small, this looks more and more like a delta function. In other words, when the imaginary part goes to 0, this becomes a very, very narrow resonance, which is very, very long-lived. But if gamma and 1 over gamma are of the same order, then this doesn't look anything like a real resonance you can attribute to which you can attribute physical properties. But of course, we know that the spectrum here consists of absolutely stable particles. And so all these gammas are 0. And what you get is a sum of delta functions. Is that clear? Now, one thing you could ask me is that I haven't been very precise about what omega and k are. Because I'm computing this correlator at null momentum, because I want to get the spectral function for null momentum, the only way I'm going to get delta function contributions, in fact, any contribution to this spectral function, is if the spectrum contains excitations that have omega equal k. Is this clear? Because I want to evaluate this quantity at omega equals k, okay, at null momentum. And so unless this vanishes somewhere, I'm not going to get a pole of this form. But remember, I emphasized yesterday, when I plotted the dispersion relation for you for the mesons, omega as a function of k, we saw that it starts here with a mass gap, and then it goes up, but it does so below the light cone. And so it always crosses this point. So there's always, for each meson, there's always a state of that meson with some momentum and some frequency such that omega is equal to k. So this is what gives a delta function contribution to this spectral function at null momentum. Is this clear? Good. The second comment before we actually do this calculation is that I will not be able, I'm particularly interested in computing this correlator and examining its dependence on the quark mass. Why? Because in this phase, even though you still have a parameter which you call the quark mass, which is a parameter in your bare Lagrangian, in your microscopic theory, this is not the mass of a physical excitation. I'm trying to argue that there are actually no quasi-particle states. Okay? It's just a parameter on which the physics depends. So I'm particularly interested in examining the dependence on this parameter. And I will not be able to compare what I get to calculations in perturbative QCD, which would have been interesting. The reason I won't be able to do that is because in perturbative QCD, one always assumes, when one does this type of calculations, that the thermal mass of your particles, quarks, gluons, etc., is much bigger than the bare mass. This is an assumption that one always makes. So in QCD, this, which is of order root lambda times t, is always taken to be, this is M thermal, much bigger than the bare quark mass. So effectively, the bare quark mass is always set to 0 in perturbative calculations. Now, regardless of the range of temperatures to which this approximation applies, the very nature of the approximation means that you're assuming that there are quasi-particles to which you can attribute meaningfully a thermal mass and other physical properties. And we'll see that's not necessarily the case at strong coupling. Mukun.
So do you expect poles for all the mesons? The mesons we are talking about so far were scalar mesons.
Yeah, there are also vector mesons. You're right.
You're
They have to have the right quantum numbers.
Spectrum, the poles they're talking about are poles for vector mesons.
Yes.
Because
Yes.
those are the only ones that we
That's right.
couple to J.
That's right. Yeah. Okay, so how do we do this calculation holographically? Well, we just need to remember a couple of things. We need to identify what the dual to the operator at hand is. So let's remember that remember that in the gauge theory, in the presence of NF quarks, quark flavors, there is a global UNF symmetry that rotates the quarks into one another. This is essentially SUNF cross U1. This U1 will come up again later. We'll call it U1 baryon or U1 quark, because it's the symmetry that rotates the quarks by a phase. And it's the one that you would like to gauge if you were to construct an SUN cross U1 theory by coupling this to a dynamical photon. Okay? So this global symmetry in the string description is a gauge symmetry. This is always the case. Global symmetries in the gauge theory are gauge symmetries in the bulk. And it's just the gauge symmetry associated to having NF coincident D7 branes. So this is a gauge symmetry here. So for each of these generators, there's a gauge field living on the 7 branes. It's just a non-abelian theory living on the 7 branes. And in particular, this one corresponds to the overall U1 living on the 7 branes. So the conserved current, J mu, let's call it J mu quark, or J mu electromagnetic, or J mu baryon, whatever you prefer. This conserved current is dual to this field. So if I want to calculate a 2-point function for this guy, that's given, as usual, by taking the effective action for the D branes, evaluating that on shell for a fluctuation of this field, and taking 2 functional derivatives. Is that clear? Good. So doing that takes some work, and you have to do it numerically, because you can't even solve, first of all, for the embedding analytically, and then you have to look at fluctuations around that embedding and so on. So I'm going to tell you what the result is. And so I'm going to turn this on. Are there any questions so far? Yes.
Just wondering, isn't that a 7-dimensional gauge field though, which would, from the point, if you go to from the 4-dimensional point of view, be like what's it called, non-dynamical?
No.
So you have this infinite radial direction, which you kind of have.
No. Because first of all, that's a good question. So first of all, you're very right that on the 7 branes there's a 7 plus 1 dimensional gauge theory living there. But of course you can decompose A in components. So you have A mu along the 4 dimensions of the gauge theory, A rho, which is a radial component, and then A alpha, alpha I, which are the 3 components along the 3-sphere wrapped by the 7 branes. And each of these in turn you can now expand, for example, in spherical harmonics on the S3, and expand in normalizable modes along the radial direction. Okay, so that's going to give you a whole tower of Kaluza-Klein modes, some of which will behave as vectors, and some of them will behave as scalars from the 4-dimensional point of view. And the one, just a second, the one that's dual to J mu is this one, and in particular the 0 mode of that one along the internal directions.
But wouldn't you have to do then, so you sort of dimensionally reduce, so you kind of do an integral over the remaining directions. The radial direction is infinite, so you get infinite factor for your coupling constant, and you have non-dynamical theory then.
No. Do you agree this one is dynamical before I reduce?
Yeah.
Do you agree if I look at the 0 mode that's still dynamical?
Not really, I would say. Is it?
Why is that non-dynamical?
But I would have thought that basically, if you just look at the action, you have an integral over 7 dimensions. You basically want to keep 4 for the action. The other 3 you have to somehow integrate out. And one of these is infinite, so you get an infinite factor in your action.
Maybe a way to clarify the confusion is that you should think of ADS as a box, really. And I'm looking at normalizable fluctuations. So for those ones, it's really like putting periodic boundary conditions, if you like. So in a way, this infrared divergence that you're talking about, this volume divergence, does not make it non-dynamical. Any other questions? Okay, so let me explain what this plot is. This is a plot of the spectral function, the trace of the spectral function, which is what we need to plug in here, in some units to make the whole thing dimensionless, as a function of what I'm calling omega here, which is a dimensionless energy, k naught divided by 2 pi times the temperature. And these different curves correspond to the result for the spectral function for different values of little m, where little m is another dimensionless ratio, which is the meson mass divided by the temperature, or if you like, mq divided by root lambda t. Okay? For each value of the quark mass, you have a different D7 brane embedding, and for each of those, you can then calculate what the spectral function is. And that gives you the dependence on the quark mass. So the curve up here is for massless quarks. And this curve, I don't know if Larry Yaffe showed this result, but for null momentum and massless quarks, this is exactly the curve. And in fact, this one you can calculate analytically. Exactly the curve he could have shown, or he showed, I'm not sure. But then the result changes as you increase the quark mass. And this one up here, or down here, I should say, corresponds to the maximum value for a given temperature, the maximum value of the quark mass, for which the embedding is a black hole embedding. If you go to higher, larger quark masses, you jump. There's a phase transition, remember, to a Minkowski embedding. Okay? So only for this range, there are black hole embeddings. And what you see is that in this spectral function, there is absolutely no trace of any narrow peak or any structure whatsoever that suggests any interpretation in terms of quasi-particles. However, remember that as you keep increasing the quark mass, thermodynamically, there is a phase transition, but you can ignore that and calculate this correlation function, this spectral function, for embeddings that approach more and more the critical embedding, even though they are first metastable and subsequently unstable. But you can ignore that fact and see what you get, okay? So and what do you expect? You expect that as you approach the critical embedding, resonances should develop, because if you approach the critical embedding from the other side, you know you're in a Minkowski phase, and there you have absolutely stable, narrow delta function-like particles. So indeed, if you take this embedding and you approach this one by increasing more and more the quark mass, this is what you get. So the red curve is the same one, the last one in the previous plot. Okay, the maximum value of MQ for which you have a stable black hole embedding. Then the green curve, you see it's starting to develop some structure, is a slightly bigger quark mass. The blue one, which already has clear peaks, is even closer, and the purple one is even closer than the previous one. So you see that clearly you're developing delta function-like resonances, as you would expect. Is this clear? Good. So hopefully you're convinced that in this phase, if you stay, if you focus on stable embeddings, then there are no, at least I don't see any evidence for to think of that as a gas of quasi-particles. Now, there are a couple of other comments that I want to make before moving to the next topic, which is that in the previous plot, for example here, I have chosen these dimensionless variables, like little m, for example, omega, and I have made these dimensionless by dividing by powers of t as well. In particular, omega is the photon frequency made dimensionless by the temperature, and little m is the quark mass made dimensionless by the temperature. So when I plot these curves for constant m, that means that I'm varying both mq and t to keep little m fixed. But in a real experiment, like at RIC, that's not what happens. What happens at RIC is that you collide these two heavy ions, and the temperature, first of all, will change in space and time because there's some hydrodynamic evolution of this fireball. But the quark mass is fixed. It is what it is. And the photons that you measure, okay, have whatever energy you decide to focus on. So in a real situation, it's K naught and MQ that are fixed, and it's the temperature that changes. So this doesn't give you a very good idea of what's going on because both variables are changing at the same time. Okay, so you should make a three-dimensional plot and slice it in a different way. So if you do that, I want to show you what you get. This is the total photon production per unit photon energy normalized by some constants, in particular by the photon energy squared, and a reference temperature that, for convenience, I've taken to be the deconfinement temperature. So this is around 175 MeVs, but it's fixed. So whatever temperature is such that QCD deconfines at that temperature. Okay. And over here, what I'm plotting is this reference temperature over the real temperature. So at RIC, what happens is that you start at a high temperature. So at RIC, you start over here, about twice the deconfinement temperature, and then you cool down. Whereas LHC, which will also run heavy ion collisions, will reach approximately, it is expected, about 4 times TC, or T deconfinement. So it will start here, and it will cool down. And this graph corresponds to photons of energy 100 MeV. This one here, which you see is very similar, corresponds to photons of 1,000 MeV. And so what I want to point out, and then these two different curves correspond to the prediction you would get from this model for quarks with masses equal to the U quark, the D quark, the S quark, and the charm quark. Is this clear? And so what I want to point out is that you could have thought that, for example, because the charm quark is so heavy, okay, it's 1.5 GeV, at temperatures of about, say, 300 MeV, the contribution to photon emission, you could have thought, is going to be Boltzmann suppressed, exponentially suppressed, and hence completely negligible. You could have thought so. That's not what happens, because you see that even around this temperature, it is smaller than the lighter quarks, but it's not exponentially smaller. And if you think about, for example, the S quark, which is, of course, still much heavier than this, the contribution is quite similar. So that's a universal result for all these models. The precise numbers may change, but the fact that you cannot forget about heavy quarks is a universal prediction, again. David?
In each of these lines, you put NF equals 1 and then put in the specific quark mass. Is that right?
NF is here, so NF doesn't enter this result. NF only enters this result through this normalization.
I see. So you should just be adding all these lines together.
Exactly. Yeah. Are there any questions about this? Okay, so this would still not be enough to make a prediction for what you're going to measure at one of these collisions. Because here, what I'm giving you is, say, for a given temperature, and given quark mass and given photon frequency, what is the rate of photon production? But of course, in a real collision, the temperature is going to change over space and time as this thing expands and cools down. It's a very complicated process. And so what you would need to do, yes?
So if you were to really include all 4 quarks together, you would need to separate your D7 brains.
Right.
And then look at that embedding. And
Right.
then you could get quark interactions. The 1D7 brane could affect another.
Not at the quadratic order, which is the only thing you need to the for the 2-point function.
Quadratic in E squared.
Quadratic in the field strengths, in the gauge fields.
You can tell me it was 1 over n squared.
Yeah. So what you would need to do is take these results and plug them into a hydrodynamic simulation for the space-time evolution of the plasma. And not only that, but moreover, experimentally, there are lots of sources of photons in these collisions. For example, the ones you're interested in are the photons that come, what the so-called quark-gluon plasma photons, which are the ones that really come, that are emitted when these colliding ions form this fireball and it reaches thermal equilibrium. Once it reaches thermal equilibrium, it stays like that, at least local thermal equilibrium, for a little while it's expanding, and eventually it hadronizes. Okay? So it's only while it's really a deconfined, equilibrated plasma that this calculation applies to, because I've assumed thermal equilibrium. But of course, in the initial collision between these heavy ions, there's parton-parton collisions, which emit photons. When it hadronizes, it produces pions, which also decay and give you photons. So there are lots of sources of photons. And experimentally, it's really hard, or quite hard, to distinguish a photon coming from one source and a photon coming from the other one. So unless you can do that, you know, computing these guys is not going to allow you to compare with experiment. But that's not my job. Good. Any questions about that? Okay, everybody's sleepy. So let's talk about the last topic, which is finite baryon number chemical potential. So let me get rid of this. Yes.
U1 current you compute is like the current is a 2-point function of is a global U1 from the QCD.
Right.
So can you repeat like the argument why you expect this to give you like results which resemble somehow like the local U1 from?
Yes, because the difference between this, which assumes you have just an external, if you like, photon, a non-dynamical photon, and this, which is with a dynamical photon, it comes at higher orders in E. So to leading order in the electromagnetic coupling constant, the two results are the same. Because the only difference is when you have these photon loops here, which contribute, they always come with some power of E squared, in fact. Is that clear? Good. So I can erase this bit here. So what's the motivation for looking at finite chemical potential? The motivation is that not only we want to understand QCD at finite temperature, or the vacuum of QCD, we want to understand the entire phase diagram. So that means that we need to understand finite temperature, which, as you've seen, is relevant for Rig physics, for example, and the LHC, but also finite baryon number chemical potential, because that's relevant, for example, for neutron stars. Neutron stars are very dense objects, at least in the core. And so there, you can't ignore the fact that there is a finite density, baryon density, or equivalently, a finite chemical potential. And again, the lattice at finite temperature is good for some quantities, like thermodynamical quantities, and not for others. But here, it's even worse. It's hardly good for anything, even though there's progress recently. But it's very hard to do lattice simulations at finite chemical potential. And so again, anything you can say coming from analytic methods is always welcome. Now, instead of working with the chemical potential for baryon number, I will work with, which is completely equivalent, with chemical potential for quark number, which is just mu b divided by nc. In other words, the energy cost of introducing a quark is the same as that of a baryon divided by the number of quarks in a baryon. And of course, the quark density is equal to nc times the baryon density. So how are we going to modify our setup to introduce a finite chemical potential? Well, again, I don't know if I have the picture somewhere here. Yeah. So I can just refer to this picture. Very cleverly, I put a Q superindex here. So what's really the quark number, or the chemical potential for quark number? Well, quark number is a conserved quantum number. And again, remember, if you have a theory with NF quarks, all with the same mass, you have this global symmetry. And the U1, the overall U1 in this symmetry is what you would call either U1 electromagnetic, if you assume that all quarks have the same charge, or literally the U1 quark, or up to a factor of NC baryon number. This is what's called literally baryon number in QCD. Okay, QCD has this, for example, QCD with two flavors, U and D quarks, more or less of an equal mass, has this U2 symmetry that rotates one into another. And the U1 part is the one that rotates all the quarks with the same phase. And that's the conserved quantity associated to that symmetry counts the number of quarks. Okay, it's a number operator. And it has a conserved current associated to that. And that's what's called baryon number or quark number. Is this clear? So what does it mean to introduce a chemical potential for quark number? Well, it just means that you take your original Hamiltonian, or the action for your system, and you modify it by adding a term of the form mu times J naught, where J, so this is JQ. Let me put it like this, JQ 0. So it's the time component. The time component of a current is precisely the charge density. So you modify your Hamiltonian density by introducing a term of this form, which means that there's an energy cost in increasing the charge density proportional to mu. So that's what the chemical potential counts. How much does it cost you to introduce an extra quark? And of course, what you call the charge density is just the expectation value of the charge density operator in some state. So what do we have to do if we want to describe now the same theory but modify, deforming the theory by adding an extra term to the action? Well, we know we have to turn on a non-normalizable mode for the operator dual to the, for the field dual to the operator we are deforming the theory with. But remember, this operator is dual to the gauge field living on the 7 branes. So all we have to do is to turn on now, if you like, a vacuum expectation value or a non-zero value for the time component, because we're turning on the time component here, which at infinity is going to have a fall-off dictated by two quantities, the non-normalizable part and the normalizable part. So this will fall off as mu q up to a constant. This quantity here will be proportional to the quark number, to the chemical potential, plus nq divided by rho squared plus subleading terms. And remember, this is the non-normalizable part, and this is the normalizable one. So this is the deformation parameter, and this is the VEF. of the operator. Now, this A naught, given the symmetries of the problem, turning on a chemical potential doesn't break rotation symmetry in the gauge theory directions, because I'm just turning on the time component, okay? And moreover, it doesn't break any of the internal symmetries, any of the rotations on the 3-sphere wrapped by the 7 branes. So the only possibility for this A naught, the only possible dependence for A naught is a dependence on the radial direction along the branes. That doesn't break any symmetries. Or if you like, in other words, turning on A naught means you turn on an electric field on the 7 branes, and this electric field has to be radial. So this leads to E sub rho. Is that clear? Okay. Now, the first thing you realize when you think about this is that if you turn on a radial electric field, then the only type of allowed embedding is of black hole type. There are no Minkowski embeddings with the following caveat only. So let me explain this. If you try to turn on an electric field, a radial electric field, on a Minkowski embedding, then you run into a problem because the flux, because it's a radial electric field, the flux, when it reaches this point, the tip, has nowhere to go. Or in other words, the only way to turn on an electric field, a radial electric field, on this topology is to introduce a source or a sink for the electric field at the tip of the branes. If you don't do that, then this is not an allowed configuration. It's not a solution of the equations of motion. Now, one possible way out is to really introduce a source, which could be, for example, a baryon. Okay, a baryon is a source for this because it's a bound set of n quarks. Okay, and remember, the electric field is associated to the quark density. And I will come back to this a bit later. But for the moment, we'll see actually that the result seems to be that there is no baryon. So for the moment, let's assume we don't introduce a source. If we don't do that, then these embeddings are not allowed. And there's a very good physical way of understanding this. This physical way is the following. How would you actually physically induce this electric field? Well, remember, we are trying to turn on a non-zero quark density. But the quarks are just strings, remember, that stretch from the tip of the branes down to the horizon. So what happens, this is something that's very easy to check, is that the tension of the string always overcomes the tension of the D7 branes at the tip. So this always overcomes this other one. The reason for that is that the local tension at the tip, or near the tip, so let me zoom into here for a second. So suppose you have, this is the tip of the branes, and this is where the string is attached. The tension here, the effective tension at a given position, is proportional to the tension of the 7 branes times the cross-section. Okay? If you like, it's the energy per unit length. But of course, this cross-section is always going to 0 at the tip. So there is no way to balance the tension of the strings with a configuration for the 7 branes of this type. So physically, what happens is that if you try to attach the strings to the tip of the brains to source this electric field and induce a non-zero charge density, that will always pull down the tip of the brain. And it will pull it down in a way that it will actually fall through the horizon, and the only thing that will be left behind will be these electric flags. Is this clear?
But on the argument on the right-hand side, you haven't used the electric field. I mean,
What are, sorry, say again?
is it an argument about tensions without saying anything about electric fields? So it's kind of generic argument. And then on the right-hand side, on the left-hand side, you have electric field.
Over here?
Yeah.
Yeah, this argument is independent of the presence of the electric field. It's just based on the statement that the cross-section is going to 0. So you just can't balance the tension. There could be an electric field here if you like, which you know there will be because the endpoints of the strings are sources for the electric field.
Isn't this just a baryon spike, which is the same thing as a string but in a different way?
Say that again?
Isn't this just
Yes,
a
this is a
baryon
baryon spike, exactly.
It's really the same thing as the string, just
Exactly, yeah. That's one way of understanding it, yes.
what's the field theory reason that you can't turn on chemical potential in this?
Wait. No, wait. What I said, and I'm glad you asked this question because there's been a lot of controversy about this. So, the statement I made is, if NQ is non-zero, then Minkowski embeddings are not allowed. I did not say that if mu q is different from 0, then Minkowski embeddings are not allowed. I did not say this. I'm not going to say that. And we'll see why in a second. Okay? Because if you turn on a chemical potential, that just means that you're turning on the first part, the non-normalizable term in A0. But there is an exact solution for Minkowski embeddings that has A0. So if mu q is different from 0, then both Minkowski and black hole embeddings are allowed. Because I can take a Minkowski embedding. Suppose I give you a solution with 0 chemical potential and 0 density, a Minkowski type embedding. Then I can take that and add to it a constant A0. The field strength, the electric field is 0. But there's a non-zero A0. So the fact that the electric field is 0 means that this still solves the equations of motion, because in the equations of motion for the 7 brains, it's only the electric field that enters, not the potential. So I can turn on a non-zero A0 and still have a solution to the equations of motion.
But isn't that pure gauge?
No, because at infinity, the non-normalizable mode is not pure gauge. If you like, this is a Wilson. You could think of it if you compactify, for example, the time direction. This is a Wilson line.
Yeah, the confusing thing is, generally if I have a non-normalizable mode, it has to give me a wave.
No,
Turn on a source,
no,
why not?
that's not true, and I'll tell you why in a second. And that's not what you expect. Because, for example, even in QCD, you know that if you're at 0 temperature, strictly 0 temperature, and you turn on a chemical potential, until you reach the mass of the lightest nucleon, you don't induce a density.
But let's do this discussion in the context of ADS-CFT. Anytime
Yes.
I have a non-normalizable mode, I was under the impression that you do have to have a wave.
That's a misimpression. This is a counterexample to that. So let me proceed a little bit, and I think I'll possibly clarify your question.
Is the fact you have scalar superpartners for your quarks, I mean the physics is very different here from
Absolutely, I'll come back to that. Yes. So
don't form a Fermi surface. Is that
You
right?
don't.
You just get a
you
boson.
don't. At least that's, I haven't analyzed it in detail, but I'm convinced that's what happens. Okay, so coming just to address a little bit more Mukun's question. What do we expect? So at least at 0 temperature, your expectation should be the following. It should be that for values of the chemical potential below the quark mass, what you gain by here, if you look at the Hamiltonian, what you gain by introducing a quark, depending on the sign of the chemical potential, you may decrease the energy. For example, if the sign is a minus sign, you may decrease the energy, but you have to pay a price, which is the mass of the quark. So there's a trade-off, and unless the chemical potential is big enough, it's not advantageous energetically to really condense some charge. So for values of mu below the quark mass, you should expect that NQ is going to be 0. And so that you will be in a Minkowski embedding. Whereas once you reach this threshold, then it's advantageous to condense some charge. And so here, NQ is going to be different from 0, and you will jump to a black hole embedding. And so you should expect a phase transition at 0 temperature, and then for any other temperature, you may expect this to extend into a line of phase transitions at different values now of mu. Okay? And this is exactly what happens. If you compute the free energy for black hole embeddings and Minkowski embeddings as a function of chemical potential, quark mass, and temperature, you can look and see for each of the value of those parameters which one has the lowest free energy. And that's the one that's thermodynamically preferred. And so with that in hand, you can draw a phase diagram, which I'm going to draw for you. So if you plot T over m gap, as usual, and here you plot mu over the quark mass, then as I said, when mu reaches mq, there is a phase transition, and in fact that extends all the way down to here. So here at mu equals 0, what you have is the usual phase transition as a function of temperature that we've been studying yesterday. So this point here corresponds to what we called T-fan. That was the temperature for the phase transition at 0 chemical potential. I'm plotting this. So in this phase, this is the Minkowski phase, and NQ is 0. And this is the black hole phase, and NQ is different from 0. So let me make a number of comments about this. First of all, the phase transition is first order. For the same reasons it was first order in the absence of a chemical potential. For example, the entropy density jumps discontinuously. The charge density jumps discontinuously. So this is a charge condensation phase transition. The meson spectrum also changes discontinuously. It's discrete here as usual. There are no quasi-particle excitations here. You also note that if you go to values of the chemical potential above the quark mass, then there is no phase transition as a function of the temperature. Over here, if you start here, you hit the phase transition, but over here there isn't. As I said, in the limit of 0 temperature, so on this axis, this phase transition happens exactly at the value of the chemical potential equal to the quark mass. And presumably the reason for that is supersymmetry. So let me elaborate a little bit on that. Remember, or I should rather say, let me state, that if you have at 0 temperature, remember that these 7 branes do not get deformed because supersymmetry is broken by the temperature. So this system is a 1/4 supersymmetric system. If you now add fundamental strings, that becomes a 1/8 supersymmetric system. In other words, D7, D3 branes, and fundamental strings oriented as it is indicated here is a supersymmetry preserving configuration. And so what that guarantees for you is that what I called the constituent quark mass is equal, because the D7 branes do not deform, to the quark mass. This is not true at finite temperature, because remember, in that case, the D7 branes deform, and so what we called the quark mass is the bare quark mass, is the asymptotic distance, but the constituent quark mass, in general, is smaller. Yes? So, if you're very hopeful, you might expect that actually this line of phase transitions, in other words, for a given temperature, the value of the chemical potential at which the phase transition takes place, okay, this line is, you can specify it by giving mu as a function of temperature. This should correspond more or less to the value of the constituent quark mass at that temperature. Let me say this again. Take a given, fix the quark mass and fix the temperature. Okay? And look at a Minkowski embedding of this type. We are asking at what point we jump from here to here at a given temperature. Okay? So we fix the temperature and the quark mass, and we start increasing the chemical potential. At what value do you expect that you will jump from this to a black hole embedding? That means jumping from non-zero charge density to, from zero charge density to non-zero charge density. So it has to happen when it's advantageous to form a quark. Okay? And you may suspect that that happens exactly at the value of the chemical potential equal to this energy, because that's the energy of a test quark. And indeed, if you calculate that, you find a curve that is indistinguishable from this one, except all the way down here. So this curve is the constituent quark mass divided by MQ as a function of temperature. Whereas the other one, the one that I had here before, remember, that's mu critical at the phase transition divided by MQ as a function of temperature. So what this corroborates is my statement that you start condensing charge at the point at which introducing just one unit of this charge is equal to the mass of that charge. Okay, so the energetic trade-off is exactly in equilibrium there. However, I should say that this agreement over here at zero temperature is presumably due to supersymmetry. But away from that point, this agreement is much better than you are actually entitled to expect, because estimating this energy by saying that I look at a test string in here and I look at the energy of that test string ignores the fact that when I jump from here to here, I'm not just adding a test string. This phase transition is a phase transition in which I condense a macroscopic, not microscopic, macroscopic charge density. And so, for example, this test string calculation ignores effects such as the deformation of the branes when they fall through the horizon, which is when they undergo this phase transition. Is that clear? So it is surprising and rewarding, but it is better than you should have actually expected.
May I ask a question about stability? Because, again, because you said that this constituent quark is basically also a source, and wouldn't it also pull down the brain? So it's not stable, right?
Absolutely. That's why I'm trying to emphasize that that's a test string calculation, if you like. It's an estimate by ignoring the real dynamics of what would be the order of magnitude of the cost in energy of introducing an extra quark. But of course, as soon as you really look at the details, what happens is that there is a phase transition and you induce a macroscopic charge density. But nevertheless, the value of the chemical potential at that phase transition happens to coincide more or less with your naive test calculation.
And so you cannot be in that region of that phase diagram, right?
Which one?
Well, basically the one where you would have these constituent quarks, right?
So as far as the phase diagram goes, there are two phases. One where, there is no charge density and you have Minkowski embedding, and one where there's a black hole embedding. All I'm saying is that one way to understand where the phase transition takes place is to think naively about the cost in energy. Okay, any more? Muku, did I answer your question?
I think I agree with the statement that non-normalizable modes don't necessarily lead to normalizable modes if they're constant.
Yeah.
But I'm not convinced that this is equivalent to turning on a Wilson line. I think it's still pure gauge. Your time direction is not compact. If your time direction is compactified, then I'm concerned about your black hole embedding. Because then you don't have your brain going through a horizon. There is no horizon. The space ends at the bottom of the throat of the cigar.
But in the black, in the
if you Euclideanize, if you are thinking of
if I Euclideanize this configuration, but the brain is falling through the horizon, so it reaches all the way down the cigar.
Does it smoothly cap off at the top, bottom of the cigar?
Yeah, I think it smoothly caps off because the brain wraps the time circle as well. So the brain extends in the radial direction and wraps the time circle. So yeah, it is smooth, yeah.
But then, what about your analysis of the?
In fact, sorry, since you asked me this, let me. Sorry, you were referring to black hole embeddings or Minkowski embedding?
I'm just asking whether A naught is pure gauge or not. Back to my question. If you're in Minkowski,
A naught at infinity is not pure gauge.
Minkowski signature.
In either.
Okay, we should talk about it.
Okay. So let me, actually one of the things that you should be objecting to is how come, so there's a little puzzle, which is at zero temperature, it is reasonable that if I turn on a chemical potential, I don't induce any charge density, it's strictly zero, all the way up until the time it is energetically favorable to introduce an extra quark. But if you are at any finite temperature, then at any finite temperature, what you expect is that there will be a thermal gas. It might be not very dense, but there will be some thermal density of both quarks and antiquarks, just thermal per production, okay? So if you turn on a chemical potential, you favor, say, quarks over antiquarks. So at any finite temperature, if you turn on a chemical potential, why isn't there perhaps a small, but non-zero, density over here? Is the puzzle clear? The answer to that is that that is exponentially suppressed in the tooth coupling. And the reason for that is that, remember, the order of magnitude of the temperature in all these phases, okay, this is the low temperature phase, is of order T1, which, remember, is of order mq over root lambda. And so this thermal density, this Boltzmann factor associated to this thermal gas, goes like e to the minus mq over t. But this, of course, if you replace mq and t of order T1, which is mq over root lambda, this is e to the minus root lambda. So indeed, you should expect, strictly speaking, some non-zero density, but it is exponentially small at large tooth coupling. And these effects are not captured by the approximation in which we are working in. Okay, this is not even polynomially suppressed, it's exponentially suppressed. Okay, so I think I have 2 minutes left. I was planning to talk about baryons, but I think we don't have time for that. So let me maybe just make a couple of comments, and then I'll conclude, and we can take questions. So the couple of comments I have, was I have a couple of comments and 3 more comments. The first couple of comments are caveats. So caveats about using this setup to compare to QCD. The first one is what David was pointing out, which is that this theory has not only quarks in the fundamental, but also scalars. Bosons, so not only fermions, but bosons too. So in QCD, because the quark number, or the baryon number, is a quantum number that's only carried by the quarks, and these are fermions, if you turn on a finite density, these fermions obey an exclusion principle, and so they form a Fermi sea. And the boundary of this Fermi sea is a Fermi surface that has a lot of interesting physics associated to it, okay, that we would love to understand. Unfortunately, this model has scalars, and the scalars also carry this baryon number. And so when you turn on a chemical potential, what tends to happen is that the scalars condense, Bose-Einstein condense, and they don't build a Fermi sea. So the physics at finite chemical potential may be radically different in this model and in any other model, be it QCD or any other model with only fermions in the fundamental. So this is a caveat you should add to all the usual caveats about comparing ADS-CFT with QCD. It's specific to finite chemical potential. This problem is absent in the Sakai-Sugimoto model with D4, D8, and anti-D8 brains that you heard about last week. And recently, there's been some progress about understanding that model at finite chemical potential. So if you're interested, you should definitely go and read those papers.
Who are they by?
So there's been a lot of them. I would particularly encourage you to look at the one by the UBC group, the Vancouver group. This is Moshe Rosali and Mark van Ransdom and 2 students. And there was another one by the Israeli group, Oren Bergman and Gilad Lipschitz and somebody else whose name I'm forgetting. And then the second comment is that even putting that aside, a lot of the phases at finite density that QCD is supposed to have their existence and properties depends crucially on having 3 colors and 2 or 3 flavors. Okay? So clearly, if you're working in a proper approximation where NC is much larger than NF, you're not going to see those, such as color flavor locking phases. Perhaps superconducting phases you could see, but you should also have that in mind, that caveat. And even, so you could ask whether a back-reactive solution in which you don't treat NF as a small perturbation, but you keep it as order NC, whether that could help. But that's not even clear, because, as I said, those phases in QCD depend not only on having NC of order NF, but on both of those being 3, or 3 and 2. So there could be a stumbling block there, I'm not sure. But in any case, given that we have no other methods, I think anything one can say analytically is really welcome. And then let me just conclude. The first, with future prospects, one of them was, as I said, a lot to do at finite density. I think that's going to be a really fruitful direction. The second one is the observation that unfortunately nature has only given us 1 quark gluon plasma, the QCD SU3 plasma, but it has given us a lot of condensed matter systems, and a lot of those are strongly coupled, okay? And they live in 2+1 dimensions, 1+1, even 3+1. So here's a wonderful method to address strong coupling physics in physical systems, and we have a lot of condensed matter systems. So one really interesting direction is to move away from quantum field theory and try to do condensed matter physics. And then finally, I just want to point out and remind you that LHC is going to run heavy ion collisions for 1 month a year. And I think everybody's quite convinced that the first interesting results from LHC will not be in high energy particle physics, they will be in heavy ion physics. And so if you think about what's been learned at RIC, then hopefully at LHC we'll learn even more. And then the challenge that I think is very important is whether we can actually, before they do it, can we make concrete predictions, at least at qualitative level, that nobody else can make using other methods for LHC before. So we're really good at making postdictions, but it would be good to make predictions. Okay, so I'll leave you with that. Thank you.
Questions? Comments?
Yes.
The effect that you described where the tension of a string pulls down the D7 brains into the black hole horizon, does that mean that you never get sparks occurring in the Minkowski phase?
You never get a macroscopic density. So this NQ, I didn't emphasize that, but NQ, if you plug in the numbers, scales in this phase, scales as NF and C times some dimensionless quantities. So you never get something of this order. But of course, anything that's suppressed with respect to this, say it's of order 1, like a test string, you should indeed think of that as a perturbative excitation of the Minkowski phase. But you will never, so it's a microscopic excitation, if you like, but you will never see a macroscopic density, which will be represented by an electric field on the 7 branes on the Minkowski phase. That's not allowed, but you can still allow things that are suppressed by powers of 1 over n. Those will not pull it down.
Thanks. More questions?
You identified some particular system in solid-state physics, which is suitable for this kind of analysis, or you are still looking?
I personally haven't, but my friends have. There have been papers by Koftun and Sean Hartnell and other people where they have looked at generic properties of some 2 + 1 dimensional strongly coupled systems, such as, for example, thermal properties that you can, or relationships between thermal properties that you can actually understand by using these dual descriptions. So.
Okay, well, let's thank David again for a lovely series of